to another video lecture in Math 442. This is section 6.3.4. Just one more generalization of the error analysis that we saw in the previous couple of videos. So let's get started. In section 6.3.4, we're really just generalizing the error analysis or the convergence analysis that we did in the previous couple of sections. This is going to look very similar. I'm just going to make a couple of comments to let you know that applying the Euler's method or applying a bunch of these one-step methods, say Runge-Kutta, for example, then you can always analyze them in much the same way that what we did earlier kind of works. So think about any of those methods that fit into this category as being able to be presented in this one-step form, where now this psi, it would have been just a simple Tn and Un for Euler's method, okay? Or if we were doing something else here, this would be some linear combination for all of those Runge-Kutta methods. We used a psi that was really a combination of a bunch of these different intermediate steps as you move along. And so all of those algorithms can be analyzed in the same way if you simply make a couple of assumptions. Number one, that the f that you're working with in your u prime equals f, it's got to be Lipschitz continuous in your u variable, just like before, with a particular Lipschitz constant L. And then you also need to assume that whatever you have up here as psi, that thing will also be Lipschitz continuous. It has to be Lipschitz continuous in all three variables. So it'll be a function of t and u and k. And you can see a few more details in your textbook. I don't want to belabor it too much. One comment here is that any one-step method that is of this particular form right here, well, if you evaluate psi at k equals 0, then that thing, if that is continuous in k, then that one-step method is consistent. I won't say anything more about that, just to kind of walk you through a few of the algebra details here. You write the local truncation error in much the same way that we wrote it before. It's going to look like this, only now where you saw an f, there is now this psi variable. It'll just be uglier to work with. We rewrite that equation in the same way that we were rewriting them before. UTn plus 1 is what you solve for, and you still get something in terms of u at Tn and your psi, and then your local truncation error. Form your global error in the same way. So En plus 1 is really our approximation at time step Tn plus 1 minus the true solution at Tn plus 1. So we're still starting with the same definition. We plug in our expressions from 6.17 and from what we were doing above, and then we collect all of these terms. When we collect these terms, we put our error at our nth step right out in front, and then there should be some difference between psi evaluated at your approximation and psi evaluated at your true solution, both at the nth time step. And from there, you bound your error in much the same way. You take absolute values and apply triangle inequality to get you to the next step that you see there. And then from there, I'm again looking at my Lipschitz constant. So that means that the difference between these psi's and absolute value will be less than or equal to Lipschitz coefficient times the difference in the u values. So this is exactly the same thing that we were doing before. And so what you get down to is really the same thing that we were doing before. You think of your error at the n plus first time step in absolute value is bounded by a multiplier times the error at the nth time step. And here is where k times your local truncation error at that nth step will show up. Everything else follows exactly the same. And that takes care of everything that we're going to say about how the global error analysis might go for the one-step methods that you see here, the mathematical assumptions you need, and how you recursively build up your error terms until you get to some sort of expression involving your infinity norm of your local truncation error and things like your Lipschitz constant and your final time, capital T. Thanks for joining.